welcome back. So, in today's video lecture, we will look at the list of techniques that are available to measure surface tension. So, we will continue from where we left, and then we will look at in details the working principles of a few of the techniques, right? That are quite often used, right? In determining surface tension, if contact angle is known or contact angle if surface tension is low. Okay, and let's begin our lecture. Yeah. So these techniques are widely available, right? If you want to measure surface tension, right? For example, we know Wilhelm plate, which is one of the very popular methods that people often use, right? And then we have what is known as Dunai ring. So it is Dunai ring and Wilhelm plate work under the same principle of operation, right? And only the geometry that are used are different. And apart from that, this capillary rising is a very classical method. Okay, and in this, one can measure what is the surface tension and what is the capillary radius. Okay, what is the height at which the liquid column, walks climb up the climb on the surface, right? So these things we can measure readily, and we have what is known as maximum bubble pressure. One of the advantages of this method is you don't need to know or specify what is contact angle, right? So we will see them in detail. A pendant drop and spinning drop are also, some of the techniques. Okay, one of the techniques that are also used, right, quite often, right? Depending on the conditions, right, in which we want to measure surface tension or theta, right? So in today's video lecture, we will look at the working principle of Wilhelm plate and capillary rise, and also the maximum bubble pressure. Before we even look into the overview of some of the devices, let's first ask a question. Let's first describe surface tension as a force. First, let's understand how surface tension can be regarded as a force, right? So this schematic we have also seen in previous lecture. So, but this schematic is quite easy to understand the clarity. I mean, you will get a little bit more clarity. So here, the insight that we will get into this schematic is how surface tension. So surface tension, as I told earlier in the lecture, in previous lecture, the work done by the system, right, due to surface tension. Okay, so let's say we have a container which is filled with water in this case. Okay, for brevity, this container is shown upside down. Okay, it is just kept inverted. Although it is, in reality, it is, it is just to show, the action of surface tension, so that it is very easy to capture, right? So that's why this schematic is shown. So you assume that this container is filled with water and it is kept upside down. Now this particular, so this part is this dotted line represents the thin wire, okay, which was placed at time t equal to 0, right? And you can understand this solid line represents the position of the thin wire. So, after some time t, right, after the action of surface tension, is taken place. Okay, so you can see clearly, because the surface tension acts downward in this case, this will pull this wire okay, towards the inward, right, inside, right. So as a result of which, this wire would have made some displacement, which we can say delta x, okay. So it would have made some delta x, a displacement because of the surface tension, which is acting downward, because it pulls the liquid towards it. So this thin wire, will be made to move because of the action of surface tension. So because this dotted line was initially placed at x is equal to 0, and this movement, if you can denote as delta x, right, then we can clearly say the some work is being done in this case, right. So how we can define in this case gamma as force is, let's say we know what is surface tension, right. Surface tension is nothing but force acting along the length of the surface, which is usually denoted as Newton per meter. Okay, right. So because it is denoted as force per unit length, when you multiply that with the perimeter, in this case, since we consider the thin wire, right? So it, as in a very which has got length, right? Which has got length and breadth. So here we are assuming that the width of this wire is very negligibly small. So the perimeter, although the perimeter of this should be 2 into L plus D, since D is very small, we ignore that for the time being. So you can simply multiply this with respect to the perimeter. Here in this case, perimeter in this case is simply nothing but 2L, right? So when you multiply that with the perimeter, one would get the force, right? So which will be simply Newton, right? So you can also consider surface tension. Sometime you can also express surface tension as surface energy, which is nothing but joule per meter square. Okay, you can also express surface tension as Newton per meter, or surface energy as joule per meter square. When we express surface tension as surface energy, which is in joule per meter square, you can multiply that with the change in area. Okay, the change in area is the the surface tension which is acting on the the area, right, which is along the entire wherever this surface tension is applicable, right, along the entire line of action, right. So if you multiply that with the change in area, one would get simply work done, right. I think this we have also seen in the previous lecture. So gamma dA would result in work done, whereas the displacement multiplied by gamma would result in force. So that is what exactly we captured in this equation. Okay, this is surface tension as a force. Now we can also look at the capillarity rise. We have also discussed to some extent in previous lecture. Okay, here you will see whenever you introduce solid, okay, whenever the liquid shares a greater affinity with the solid, you would expect liquid to climb up the surface because they share a better affinity with the surface. So they want to maximize their contact with surface. So in such case, you would expect elevation. If the affinity is not, appreciable, then if affinity between solid and liquid is not very much, pronounced, then in that case, you would expect depression instead of elevation, right? So in this case, we have shown an example where liquid would want to establish the contact with the solid because they share better affinity. In this case, there will be, the liquid will rise up. Okay. So now the question is, how long the liquid will, rise up on the surface? The answer is, whenever the liquid rise up due to surface tension force, there is also a counteracting force which is acting downward. That is nothing but the force of gravity. That so at some point of time, there will be balance between the two, okay? Because surface tension, causes the rise in liquid, the mass of liquid, okay? On the other hand, which would, put the speed breaker for the liquid column that is, rising up, right? So because this gravity is acting opposite direction, you would expect at some point of time, there will be equilibrium, okay? So in this way, you can expect that there will be a liquid will rise, but not to infinite distance. It will rise up to finite distance. That is dictated by the gravity, force of gravity, okay? Now in this case, if you can balance two forces, one is surface tension force, on the other hand, gravitational force at equilibrium, both will be equal. Now, additionally, what we need to also look at is here surface tension is a tangential force, but because there is an angle to it, the liquid establishes contact with some angle, one has to include the components of forces. So, using the geometric rule, we can deduce this tangential forces gamma cos theta. We'll see them in detail, right? So this is the some of the concepts. In this way, we can explain surface tension as a force. Okay, right. So now we will look at how the Wilhelmine plate is used to measure the surface tension. So basically, what we do is simple force balance, right? We just do simple force balance. So how it works is very simple. So whenever we introduce a plate, which is called Wilhelmine plate, this plate, this plate is connected to what is known as the balance, weighing balance, very sophisticated weighing balance. Okay, so what this weighing balance does is it actually takes this Wilhelmine plate, okay, measure its weight at before it touches the liquid, and and take that take into account. Take this weight of the plate as reference weight. Then when you introduce the plate and when it exactly touches the liquid surface, you would see that there will be meniscus. Okay, that's because the liquid shares greater affinity with solid. Okay, so there will be capillary rise. So because of which the water will try to climb up the surface. Okay, so in this way, because this meniscus is held up by the tension on the liquid surface, the weight which acts on this plate will be recorded by the balance again, which will be again compared with the reference weight. The change in weight, okay, that results out of this process is nothing but the surface tension. Okay, one can measure surface tension out of this. This is a simple force balance. So you can see that the weight, which is nothing but mass into gravity, can be equated, okay, at equilibrium, because one hand there is gravity which is acting downward, on the other hand surface tension which is acting upward because it shares greater affinity with the solid, okay, and it wants to maximize its contact area with the solid surface. So in this case, you have two counteracting forces. One is surface tension and another one is gravity. So when you equate both these forces at equilibrium, you can get this relation. Again, we get gamma cos theta. Okay, this is components of force, right? Because surface tension act tangentially, so perpendicular to the liquid surface, right? So you can actually deduce this gamma cos theta, from the geometric rule. You can also look at this schematic. In this schematic, it is clearly depicted. What we actually measure is the tangential force, which is perpendicular to the liquid, right, surface. So So basically, the tangential force is nothing but gamma cos theta in this case. You can get this gamma cos theta from the simple geometric rule. And when you multiply that with the perimeter, we will get the simple, we get the expression in simply in, force unit, right? So that is what exactly we do here. On the other hand, we also, can easily understand the capillary, right? Using the same principle. We do the same force balance in this case as well. So what is different in this case is simply the perimeter. It's not a rectangular anymore. Since it is a capillary tube, the perimeter which is acting, the surface tension acting along the line of contact is different in this case. So which is nothing but the 2 pi r in this case, right? So that is the only change here. You can see that. So what we can do is we can, break this mass into gravity, this equation, mass into gravity into rho Vg. In this case, we know what is the volume of the capillary tube, right? So which is nothing but pi r square h. We know what is the perimeter because the surface tension acts on the circumference, right, here. So which is nothing but 2 pi r. So that is the difference here as compared to VL plate. So simply what we will get here is the capillary rise, which is RC, is nothing but 2 gamma cos theta divided by delta P. You can also write delta P as H rho G. Okay. So using this equation, one can calculate theta if the rest of the parameter is known, or height of the column, right? Or sometimes the capillary radius. So all these 3 parameters can be determined usually using this capillary rise method. Okay, right. So now coming to the maximum bubble pressure method. This is quite simple because in this method, the advantage that we have in this method is, it doesn't require the contact angle measure. I mean, you don't need to measure or you don't need to know the contact angle. Okay. So here what we actually measure is the pressure required to detach the bubble. Okay. So pressure required to detach the bubble, will give you a relation between gamma and surface tension and the Laplace pressure. So basically the pressure, so whenever we, purge gas, okay, through the tube, okay, which is submerged in the liquid, at the end of the tube, it forms bubble, okay. As the pressure increases, the bubble grows up, okay. But at some point of time, the radius of the bubble is same as the radius of the capillary tube. At that point, one would capture the maximum pressure, okay. It can also be shown that the Laplace pressure, okay, of this spherical bubble is nothing but 2 gamma by r, which we'll also see in detail in following lecture, okay. And after this, so this is where the equilibrium between the pressure force and surface tension force both, exist, right? Okay. After that, beyond this point, as you increase the pressure, because there is, when you increase the pressure, what happens is, the bubble wants to, get released from this tube. But on the other hand, there is also surface tension, which actually pulls back, okay? There is a affinity between liquid and solid surface, which actually resists the bubble to, get detached from the tube, okay? But beyond when the pressure is, more dominant than the surface tension force, one would see that the bubble is easily released from the tube, okay? So what we can do is we can actually perform a simple force balance. because we have pressure from both the end. One is from the top through the tube, okay, from top side, that is let's say P1. The other one is aerodynamic pressure, because the tube is immersed in the liquid column, right, liquid pool. So you would have also pressure, right, from the bottom. Okay, the change in pressure, there is also another force that is acting upward in this direction, because the bubble is held by the surface tension force. Okay, so since force is acting on the opposite side, you can actually perform a force balance between the pressure force and surface tension force, which is nothing but you can when you perform this force balance, you would get finally in terms of this equation, which is nothing but P1 into pi r squared, because here pressure acts on the this top side, right? So the area of this is pi r squared. On the other side, pressure acts from the bottom, which is again nothing but P2 pi r squared. And then you have gamma, surface tension force, which acts upward, okay, which is actually pulling the bubble, okay, from getting, from detachment, right, which is nothing but gamma into 2 pi r, okay, and 2 pi r is a perimeter here. Now, when you actually perform this force balance, you will get delta P is nothing but 2 gamma pi r, and it is same as the Laplace pressure for a spherical geometry, which we will also show, in the following lecture. So, I think these techniques are, the very clear, and based on these techniques, one can measure the surface tension if theta is known, or theta if surface tension is known. In the case of maximum bubble pressure method, the advantage is we don't need to know the contact angle, okay, before the measurement, right? So one thing I forgot to mention, when it comes to Wilhelm plate, the Wilhelm plate is, the manufacturer supplies Wilhelm plate such that the Wilhelm plate is made up of a special alloy, okay? The advantage is they make contact with the water, okay, in such a way that the theta is negligibly small, okay. Their wettability with the water is very good, so that the theta is negligibly small. You can actually ignore this, this component, the component of theta. So in such case, you don't need to worry about the measurement of theta, right? All you need to do is just you need a perimeter, and you need to measure the weight of the liquid that is acting on the plate. Then one can easily measure gamma. Okay, in this case also you don't need to measure theta. Okay, with the current sophisticated instrument that we have today, you don't need to really worry about theta. And again, in the case of maximum bubble pressure method also, we don't need to really worry about theta. Okay, so we will stop here. We will continue from the next lecture. Thank you.